Guys, we've got another lab experiment to do. And this one is going to involve another cation method. What cation, you might ask? Well, that's a pretty good question. The cation that we're going to look for in this lab procedure, it's going to be calcium, all right, Ca. And we're going to be looking for calcium for a particular reason. But once again, what I want to do is just kind of touch base with you in the very beginning to let you know that this is a cation method. All right. So therefore, this is a little different than the original labs that you might have done in the ion chromatography module before. And that's because this does not use a suppressor unit. And the reason I say this, just like before, is that you want to make sure that you are picking out the correct instrument. If you're not picking out the correct IC instrument to run your samples on, then we got a problem. And you're going to be running calcium on a suppressor method, and it cannot handle a calcium method. So you've got to be very particular on which instrument that you load your samples up on, all right? So what are we going to be measuring calcium in? Well, the thing here is we're going to be measuring calcium in something as simple as orange juice. That's right. Probably one of those routine morning drinks that you swallow down before you come to class in the mornings, or those pretty good mixers that you might mix in an alcohol beverage of choice, and maybe no alcohol needed. You can do virgin drinks with orange juice, not a big deal, right? But this is basically the lab procedure that we're going to be doing. It's very food based, but we are choosing to put it into the chromatography world because not everything will fit into a nice little box for us, right? So it just so happens that this is food driven, and it just so happens that it also plays off of ion chromatography on the cation side of the house, which is really what our focus is going to be. So how much calcium is actually in the orange juice that you are drinking or that are in the different major brands across the grocery store shelf? So before we talk a little bit about the lab procedure, what you're seeing on the screen right now is a block of calcium. Yes, this is what elemental calcium looks like. It looks nothing like bone or teeth that you might associate with calcium, right? This is a metallic type of metal. It is classified as an alkaline earth metal. It has a positive 2 charge, and in the elemental form, it looks completely different than what you might associate calcium looking at. It is linked to strong bones. Studies have shown that high levels of calcium do strengthen your bones, especially when you get older. So sooner or later, it's going to happen to you. It might not be happening to you right now, but as you get older, your body will get weaker. That's just the name of the game, folks. That's how it is. So it's not uncommon for people to make sure that they are including enough calcium in their diet so that way their bones are not as brittle, or you cannot break their bones as easy, especially in our older population. All right, that can either come from food or it can come from a food supplement, but calcium is something that people look for in their nutritional diet as you age. And that's just a fact of life. All right. Calcium has a few different roles. The first role that calcium plays, it allows the blood to clot, and that's a very good indicator, because if you cut yourself, you want to make sure that the bleeding stops. And calcium really does play a role in helping your blood to stop flowing from that open wound. Number 2, it allows muscles to contract. That's also very good. A lot of times if you have muscle cramps, it could be sodium, or it could be potassium, or it could be calcium based. 3, it supports your heart to beat, not heat to beat, but it does support your beating heart to stay beating on a regular schedule all throughout the day, even while you're asleep. And finally, number 4, 99% of the calcium is located in the bones and teeth. So by far, the majority of it is included in those 2 locations, as you would probably expect, but you do have some what we would call maybe free floating calcium that goes throughout your body, but that's where the majority of it is going to be based. If you look at your calcium diet, Your calcium diet is going to include a number of different products. And we'll talk maybe a little bit about those products in just a second. But those products are going to include everything from fruits to vegetables to meat. The problem here, though, is that your body cannot make calcium. This is something that you have to get from your diet or through a diet supplement. So you're going to have to turn to food items that look like this on your screen in order to ensure that you get enough calcium that your body needs. If it doesn't get it from the food, what begins to happen is that it will start to target your bones, and it will start to rip the calcium from that source, because that's a very good source for it to get, right? 99% of it's going to be there. So if you are not eating a proper diet, or if you're not eating or taking the proper supplement, then the issue is that your body will almost self-attack itself and begin to rip calcium out in these locations that you don't want it to rip out from. You constantly lose calcium too over the course of a day. So whenever you pee, whenever you poop, whenever you sweat, and maybe all three of that's included at one stop, who knows? But when you start to do this, you begin to deplete your body's source of calcium that is available to it. And this is just a normal routine procedure that goes on every day for us. When your hair grows, when your nails grow, all of that is calcium based. So you are using calcium up when this begins to happen. So you can't do anything about it. You're going to lose calcium over the course of a day. Your body cannot make calcium on its own, so it's either going to rip it from itself, or you're going to have to supply it with the calcium deposits that it needs. And there on the screen, you're looking at a few of them. So I hope that you do not turn leafy greens and vegetables away, because that's a very good source of calcium. So keep that in mind the next time you go through a drive-thru and order a burger and fries. How much do you actually need? Well, that really depends on your gender. This is gender specific. So male and female both are in two different categories, and males have an age difference and females have an age difference. So as far as females go, the key here is 50. If you're below 50, then 1,000 milligrams per day is good for you. However, men can actually go a little bit older before they need that calcium supplement, or a little bit more. And that is 1,000 milligrams per day if you're 70 or younger. So there's a 20-year difference there. Women's bodies tend to use calcium a little bit more and tend to need calcium for specific purposes, where men do not until they get a little bit older. And that's really 20 years older on average. Females, if you're over 50, or males, if you're over 70, this is when you need to increase the amount of calcium intake per day, and you're really only increasing it by 200 milligrams. So that could be another foodstuff. It could be a supplement pill that you want to take. It could come in the form of a multivitamin, but 1,200 milligrams will be the key there for females 50 and over and males 70 and over. All right. As far as the RDA value, this might be something new to you. If so, I do want to mention it. The RDA is going to stand for recommended daily amount. Okay. So recommended daily amount basically means those numbers that you saw on the previous screen. The recommended daily amount for me would be 1,000 milligrams. So I would want 1,000 milligrams of calcium every day in my diet, or through a vitamin or supplement pill if I could manage to squeak one in. Another code that you typically see that's getting used out there is DV. And DV basically means daily value. So daily value and recommended daily amount kind of refers to the same thing. It's just a different way that they will abbreviate it and a different way that they'll talk about it. Normally, our RDAs for calcium will be based on that 1,000 milligram. As you can see from these numbers, male and female on the lower end will be 1,000, and 70 and younger and 50 and younger are making up the majority of the population in both female and male. So for that reason, the RDA is based on that 1,000 milligram total. So on the nutrition label, you're going to see maybe a percentage, and that percentage will be listed maybe, let's say, if 10%. Well, that's 10% of the RDA value. That is not 10% of the sample size of the food or drink product. All right, that's 10% of the RDA. So for calcium, that's going to be 10% of 1,000, and that would be 100 milligrams if this was calcium on a nutritional label. Okay, that is how that percentage is going to be stated. At the same time, what you're going to find on a lot of the nutrition labels are not only the percentages in terms of RDA, but you're also going to see milligrams, actual number of milligrams that's going to be stamped on these nutritional labels for you. So depending on the sample that we bring in for the lab, it could have both. It might have one or the other, but if it does only have percentage, then that is how we're going to calculate the amount of milligrams that's contained in that product per serving size. All right, so that's the key here. This is RDA, and this is a percentage on each serving size that you have, or that you're drinking or that you're eating, right? Here's a picture of orange juice, and this is what our lab is going to concern. Orange juice does have naturally calcium in it, but at the same time, we can also have orange juice that is what we call fortified, and that fortified orange juice would have additional calcium on the inside. So this is what we're going to be looking at. It's what we're going to be comparing. We're going to be comparing regular orange juice to fortified orange juice, and then we're going to calculate the amount of calcium in each of those products and just compare it to the nutritional label. Are they telling us the truth? Is that how much calcium is actually in there? Yes or no? If you don't like orange juice, though, it's okay, because on the screen you're seeing a few other products that would have calcium there, even down to bottled water, folks. So a lot of people don't think about that, but if you look at bottled water, you're going to see a lot of additives in that bottled water, and they'll tell you that these additives are added for flavor, right? And it's not uncommon to see magnesium-based salts, potassium-based salts, and calcium-based salts that get added into things just as simple as bottled water. So that is another resource that you have in order to get calcium intake. A lot of people just don't think about that, but if you buy bottled water, Aquafina, Dasani, maybe Costco brand, Kirkland, right, Sam's, Walmart brand, Great Value, whatever the case is, you're going to see those additives typically in those bottled water products. Everything from breads and cereals, typically morning foods, soy milk and almond milk have calcium added to those. Breakfast foods, juices, greens, dairy, of course, ice cream, milk, yogurt, cheese, all of those are very heavily loaded with calcium. So it's very easy to get the calcium that you need from a daily diet, as long as you're not a picky eater and as long as you're not eating the same thing over and over and over and over, right? So if you are a very easily pleased person with food, you probably are getting enough calcium in your diet on a daily basis on what you're eating right now, all right? I've mentioned this thing called fortification. Fortification is basically the concept that we are adding things into food products. And this really began in 1992. And in 1992, what we discovered is that many people around the globe, not just the United States, but around the globe, were at risk and deficient in three things: iodine, vitamin A, and iron. So those three are very simple. They should be very basic. But yet some of these countries, depending on maybe their diets, depending on their location, depending on if they're a third world country or not, would be deficient in these three categories. So as a globe, what we want it to do is improve the food products that these people are getting and eating to ensure that they are not deficient in these three simple things. So the organization that was responsible for this was the WHO, and the WHO stands for the World Health Organization. So World Health Organization, world, ding, 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 right? They were very interested in what was going on globally with food product. So they allowed and really encouraged fortification of food. And basically their definition, in quotes, the practice of deliberately increasing the content of an essential micronutrient. And it doesn't really have to be in the food product in the first place. That is a common misconception that people have. Well, basically what that means is that if our laboratory is about orange juice, I can use that as an example. I could take orange juice and I could add a micronutrient to that orange juice, something that orange juice would never have in it naturally. I could add that nutrient into orange juice, and the WHO would allow me to do that because I have deliberately put it into that product to make sure that I am addressing maybe a very small need or large need of that nutrient to certain groups of people. So this allowed the food industry to really just completely revamp their consumer products. And all of a sudden, fortification became a very common practice. The issue here, if you're not careful, is that if food companies are adding maybe unnecessary nutrients to a food product, there is a chance that you are eating those and eating other things that have high levels of that nutrient as well. And all of a sudden, we are ingesting too much of that nutrient. And this could lead to toxic side effects, right? A lot of times when people think calcium, they think of kidney stones. And that is one of the culprits that could be involved with kidney stones. So if you drink a lot of milk, if you eat a lot of cheese, don't be surprised if kidney stones will come knocking on your door a little bit later on. Is it truly calcium-based? Not really, but calcium does play a role in that whole entire process. The other argument that happens here with the WHO's decision on this is you're going to have people that say, what about human choice, right? What about me? What if I don't want to buy orange juice that's fortified with calcium? What if I don't want to buy cereal that's fortified with iron? What if I don't want these products, right? I should be able to have a choice of saying, I do not want this option because I know that I am getting enough calcium or enough iron based on my daily intakes, and I should not be forced to buy these products that are fortified and tampered with by people who are working in a lab or working with a food company. Denmark in the early 2000s actually completely banned all fortified food products to be sold on their market. You can't do that anymore in Denmark. Absolutely not. If it has the nutrient, it has the nutrient. If you are altering that nutrient through the processing technique and you are removing some of those nutrients, that's too bad for you. You cannot go back and you cannot add it in, and you cannot add unnecessary stuff into these food products that wasn't there in the first place. Now, Denmark is one of the few countries that has fully banned all fortification. Maybe many others will follow suit, but as of right now, in the United States, these products are allowed to be sold to you. So food companies can go through, add whatever they want to add into that food product, call it a nutrient, and sell it to you because they think they know better than you do on what you should be eating on a daily basis. All right. But this was the WHO's way to address nutrient deficiency. So the intention here was good, but people's response to it can sometimes be exaggerated or blown out of proportion. Here's a couple of pictures of some nutrition labels. This is actually coming from orange juice. And what I want you to focus on here is really two things. Number one is the serving size. Most serving size for orange juices are all the same, and that serving size is 8 fluid ounces, which is 240 milliliters. So both of these nutritional labels have that up there at the very top. That is a traditional 1 cup, and that's a traditional serving size for orange juice, no matter the manufacturer or the brand. But I don't really want you to look at other pieces of the nutritional label except for calcium. So if you look under this kind of main category where they can list things, to the left nutrition label, there's calcium at 27 milligrams. And then if I look at the right hand one, here's calcium, and that one has 325 milligrams. All right, so this is 27 milligrams per 240 mils. All right, or 1 cup. And this is 325 milligrams per 240 mils. The percentages here, again, that is based on the RDA. So this says 2%, right? So 2%, 25% of the recommended daily allowance. That is what that is after. So if they do include the milligrams, we typically use that first. This is a much better number, and we like to see this when it's listed. So therefore, we have a concrete number, 27. Yes, it is 27 that we can compare our results to. And good news, most orange juice brands do list calcium in this section, and they do list the actual number of milligrams per serving size, which is typically 240 mils. As you can tell, the label to the left, this is the regular orange juice that you might buy in the grocery store. And then this one to the right, this one has an extremely higher amount of calcium, right? We go from 27 to 325, and this is a fortified version, okay? Now, these regulars and fortified amounts, those might be different depending on the manufacturer and the maker, okay? That's just something you don't know until you buy the product and you look at the nutritional label. But in this example, 27 was the regular, 325 was fortified, but keep in mind, those numbers can be a little different. As far as the IC method goes, again, this is a cation method, and that cation method has to be ran on the cation instrument that we have set up in our laboratory. You cannot, I repeat, you cannot run this on the anion instruments that we have in our laboratory, okay? Calcium is a cation. It does carry a positive charge, and it actually carries a positive 2 charge. The mobile phases will also be different than the anion mobile phases. So if you put it on the wrong instrument, not only is the setup of the instrument wrong, but the mobile phases will also be different as well. And you will not get a proper separation of what we need in this orange juice sample. So make sure you're picking the right machine. Make sure that you're picking out the right mobile phases. Otherwise, you're fighting a losing battle and you're wasting time, and you're going to have to do it all over again. And finally, no suppressor is needed in this method, and the reason, it's cation based. So cations carry with them a higher conductivity. They can stand out above the crowd of the baseline, and they do not need that baseline to be suppressed. So for that reason, we bypass the suppressor. As before, maybe in another previous lab pre-lecture video, right? What happens here is that we have a column, and our sample goes through the column, and it gets sent to the suppressor, and then that is sent into the detector here at the very end. Well, in a cation analysis, what begins to happen is that we bypass the suppressor that does not get used, and we take the exit of the column and we take it directly into the detector. We do not need those other pieces in a cation analysis. Let's talk a little bit about the process here. All right, what types of calculations that I'm going to be required to do? Well, number one, we're going to have to run some calcium standards, right? And the calcium standards are going to give us a calibration curve just like before. Every time that we've done this kind of stuff, we've always made, for the most part, calibration curves using our standards. That way we know what signal relates to what concentration. When I get the calibration curve, this is going to give me the part per million, which is going to be the concentration of the sample that I analyzed. All right. Now, here's the thing. I'm going to take orange juice in this laboratory, or another fruit juice maybe, right? And I'm going to take this sample and I'm going to dilute it 1 to 100. That means 1 ml of the original orange juice from the jug will go into a 100 ml volumetric flask, and I'm going to dilute up to the line. All right, so that's the thing here. It's also one of the reasons that we do not like to use pulpy orange juice. all the pulp really gets up into the pipette and it really gets stuck and it's hard to get out and it can clog them up. So if we do purchase orange juice as the fruit juice that we want you to use, then you're going to find us staying away from the pulp versions. We're going to have no pulp in those. If it does have pulp or some kind of chunk in it, if it's not orange juice but a different type of juice, then this would easily be solved by sending it through a filter paper. But we're going to save you some time. We just don't want you to do that. So you're going to dilute it 1 to 100. So whatever ppm that you get from this calibration curve, you're going to have to multiply this by a 100 basically to get back to the starting concentration of the original sample that you used. Okay. Now keep in mind that ppm is milligram per liter. All right, so milligram per liter, let's say that I have 300 as a number. Okay, so what that means is that that's 300 milligrams per 1 liter of orange juice, if that is what my final answer is. I don't really need to know how many milligrams are in a liter, right? That's not really what I'm after here. But what I do want to know is how many milligrams would be in the 240 mils, or 0.24 liter, which is the serving size, right? That's how the nutritional label is based. That's how it calculates its number. So I can set up a simple cross multiply and divide type of problem, a ratio and proportion. So if 300 milligrams are in a liter, how many milligrams would be in my 0.240? So you just kind of cross multiply, right, in order to solve for this. So I can do that very quickly up here on the screen if you need me to. I'm going to take 300 and I'm going to multiply by 0.240 and I will get 72 equals, and then this is x times 1, which is x. So 72 milligrams would be in 240 milliliters, and hopefully that 72 would be close to the number that's on a nutritional label if this was the case. All right. Again, it's all based on RDA value. The normal number that they use is the 1000, but if we are using a nutritional label that has the actual milligram stamped on it, then that is a better number for us to use. Finally, we're then going to end up calculating the percent error. And in order for me to do that, let's say that this was actually 80. You're going to take your actual minus the theoretical over, or vice versa, over the actual, what it should be, times 100. And that's how you'll calculate percent error for these samples. All right. So basically, that's all that you got to do. We're going to bring in some juices. You're going to make sure that they are not chunky in any way, form, or fashion. If they are, just filter them. And then you'll take 1 ml and you'll dilute it to 100. You'll send it through a 0.45 micron filter, and you have to do that, the membrane or syringe filter, so that way you are not jamming up our tubing in our instrument. And then afterwards, you just put them into the auto sampler and you let the machine take over. So we're going to be analyzing a couple of different juices so that way we can compare and contrast them. And then we're going to compare that to the nutritional label of each one. All right, so good luck with the lab. The spreadsheet's fairly simple. It's a calibration curve. It's a couple of calculations that include this back dilution, and that includes the actual number of milligrams in your sample. And then finally comparing that to a percent error in the end. So if you've got questions, you know how to get a hold of me. I'm here to help. And if not, we'll see you in the lab, and good luck with your data processing.